Today we want to talk about spherical coordinates. If you recall, we're trying to describe three-dimensional space. And because it is three-dimensional space, we need three coordinates to describe all the points. Describing three-dimensional space. We have rectangular coordinates, which is a distance, and a distance. Rectangular coordinates, really good at describing rectangular things. And functions, mainly because we spend most of our time dealing with functions in Cartesian coordinates. So it's a bias that we programmed you with. Then we have cylindrical coordinates, where we have a distance, an angle, and then another distance. The cool thing about rectangular and cylindrical coordinates is that we just take rectangular coordinates in R2 and extend it to R3. For cylindrical coordinates, we just take polar coordinates for R2 and extend it to R3 with a distance. When we get to spherical coordinates, we only have one that's going to be a distance. So in spherical coordinates, we have a distance and two angles. This is as far as we can go. We can't describe specific places with three angles. If we have three angles, we have no way to track down a distance. So we're just going to have these three ways of describing R3. Three distances, two distances and one angle, one distance and two angles. So it's nice and organized. For rectangular coordinates, we have X, Y, and Z. And the Z is the same in rectangular and cylindrical coordinates. Oops, it's not X, it's R. So just to keep things organized, our rectangular and our cylindrical coordinates have that Z in common. Cylindrical and spherical coordinates are going to have theta in common, but then we're going to have a new angle. So the only holdover we have from our previous is that spherical coordinates use the same theta that we're using in cylindrical coordinates. But we've only got one thing that's a distance, which we're going to call rho, because it's a different distance from the origin to the point than we have for R. The new one that we have in spherical coordinates is phi. Our third coordinate is another angle phi. We're describing points in space, X, Y, and Z as rectangular coordinates, R, theta, and Z. That's cylindrical coordinates, where the Z is in common. And then in spherical coordinates, we have rho, theta, which is the same theta we had in cylindrical coordinates and polar coordinates, and phi, which is a new one. Let's draw a picture. Yeah, we have to reuse a lot of things. Okay. So we're going to use rectangular coordinates as the frame for this because that's the most familiar. We have distances x, y, and z. So we know that if we have a point x, y, and z, we'll use the more drab color. So we have these three coordinates, x, y, and z. Just all distances, horizontal, front to back distance, left to right distance, up and down distance. And there's our point x, y, and z. For r, theta, and phi, r is a distance down here in the xy plane or in the r theta plane. So this distance here is r down here on the floor. The angle theta, I always put the r on the wrong side. Every semester, same thing. R. Theta is the angle in standard position, so measured from the positive x-axis. And z is the same thing that we use in rectangular coordinates. So it's the same z. So now we got to describe this point in spherical coordinates. We get to use only one distance. There's only one distance that we have available. And so the only distance, the only one that we can choose is the distance from the origin to that point. So the distance from the origin to that point is the distance rho. It is kind of a P, but make it like a more like an upside down 6. Instead of dropping down and then coming back up and around for a P, instead of dropping down and coming back up around for a P, just kind of start at the bottom and go up and around. That's your rho technique. Some people draw a rho by drawing the loop first. So they start here and then they circle around and then drop down. Yeah. So you don't want to go like a letter P that has that. So you want to start at the bottom and loop up, or start at the top and loop down. You do want to decide what your style is going to be. Are you going to have like a roundy one, or are you going to have a straight up and down one, which kind of like. So we need a third coordinate here. We need this third coordinate phi. The third coordinate is going to be the angle measured down from the positive z axis. Put rho in the wrong place too. Really hard to erase without collateral damage. So rho is going to be this distance going up to the point. And phi is going to be the angle measured from the positive z-axis. So here is the angle phi. Make a phi like a little tiny empty set, but instead of an angle slash through it, make a vertical slash through it. And that'll be your lowercase phi. One of the pieces that we want to look at is this angled plane coming out at the angle of theta. I want to look at that plane from the side. I want to take this, grab it, and put it over here. I want to pull that plane out and lay it down over here, where I have my positive z-axis. Down here is going to be the xy plane. And here's going to be our point. So we can see z going up and down, but we're looking at the plane where we can see that angle phi laying flat. Because we're looking at this level, we're looking at the level of the xy plane, we can't see the angle theta. What we do want to notice is that down here on the bottom, this distance is the distance r. So down here is where we see r. So that's where we see r. I'm grabbing this plane and kind of like laying it flat, because I want to see the relationships between all these points. So for any value of theta, we can see that rho and r and phi are all related. We know that how x, y, r, and theta are related. We know that x is r cosine theta, y is r sine theta, and z is just z. We know the relationship between x and y is that x squared plus y squared is equal to r squared. And we also know that the tangent of theta is y over x. This is just what we remember from the relationship between rectangular and polar coordinates. But now we need to figure out how to get back and forth between rho, theta, and phi. Once we pull out this plane, it's a little bit easier to see that down here is r, and up here we can also see r. So we see that this distance r is opposite phi. And in this triangle, we've got z adjacent, r opposite, and rho the hypotenuse with an angle of phi. Sorry, z is adjacent to phi, r is opposite phi, and rho is our hypotenuse. So from here, we can see a relationship between r, rho, and phi. We see that r is rho times the sine of phi. We can also see how z is related to rho and phi. We can see that z is adjacent to rho z is adjacent to phi with rho as a hypotenuse. So we could say that z is rho times the cosine of phi. The theta that we use in cylindrical coordinates is the same theta that we use in spherical coordinates. We want to grab this plane, which is at this angle of theta, and lay it flat so we can see how z, r, rho, and phi are all related. Any questions? For the most part, this is the first time you encounter spherical coordinates. If you encountered spherical coordinates before you get to Calc 3, I really kind of want to meet your pre-calc teacher or whoever taught you about spherical coordinates. I want to know what class it was and when you learned about that, because that's crazy. I never would have thought about introducing spherical coordinates before Calc 3. So it kind of shows up kind of as a just-in-time thing. So, well, here's how we can describe three-dimensional space with spherical coordinates. Immediately, triple integrals. It's a little jarring. But let's think about what we want from a triple integral. A triple integral, so we have the integral over some solid W of a function of, let's use rho, theta, and phi, dv, where dv is some small rectangular solid piece of W. We're imagining dv as some solid chunk of W. We're thinking of dV as a volume, the same way we thought of dA as an area, the same way we thought dx as a length. Our normal strategy is to break dV up into, to make an iterated integral, and to break dV up into dx, dy, and dz. That works with dx, dy, and dz because we have a distance, and another distance. We had to throw in that factor of r when we had dr, d theta, dz, because d theta was an angle, not a distance. The same thing happens in spherical coordinates with our dv. If we write dv, d rho, that's a distance, no problem. I think I want separate colors. D rho, that's a distance. D theta is an angle. And D phi is also an angle. So I'm going to need some factors to turn d theta and d phi into distances. We need additional factors to turn d theta and d phi into distances. We need those extra factors from arc length to turn d theta and d phi into distances. We just have to know how far these angles, these little bits of angle are from the origin. Any questions on the concept? I want dv to be distance times distance times distance. D rho, distance. D theta, not distance. D phi, not distance. So we need to fix that. The easiest one to fix is d phi. Remember how we fixed d theta? We said how far away from the origin are we when we're making our d theta? We just use arc length. D theta, we multiplied by r. That's how far we are from the origin. That's easiest to figure out with d rho. So if I have some small change in rho, if I have some small change in rho, it's easy to see how far that is from the origin. It is, sorry, d phi. I keep switching up d phi and d rho. If we have some small change d phi in the angle, we can easily see how far that changes from the origin. That is rho units away from the origin. So to turn d phi into a length, we just need to multiply by rho. Rho times d phi, that is now a distance. For d theta, earlier we had turned d theta in cylindrical coordinates, and in polar coordinates, we turned d theta into length by multiplying by r. Unfortunately, there is no r. There's only rho, theta, and phi. There is no r, only Joule. Wait, no. There is no r, only rho, theta, and phi. So I want to turn d theta into a distance by multiplying by r, but there is no r. So we try to turn d theta into a distance by saying, I'll multiply by r. Then we look at our coordinates and we're like, oh, well, shit, there is no r. But we do know the relationship between rho, phi, and r. So we can use this relationship up here and say r is rho sine phi and multiply that by d theta. And now we have a distance. D rho, that was a distance all along. And so here is our factor dv for a triple integral in spherical coordinates. D rho times rho sine of phi d theta times rho d phi, which we will simplify. The factors that we need to turn d rho, d theta, d phi into a volume is rho squared times the sine of phi. When we're setting up a triple integral in spherical coordinates, we can't just say the function times d rho d theta d phi. The function times rho squared sine of phi times d rho d theta d phi. That is how we get our iterated integral. Comes from the fact that dv needs to be a volume, which means we need to turn d rho, d theta, and d phi into vectors. The TLDR, when you're building a triple integral in spherical coordinates, don't forget your rho squared sine of phi. I've often wondered if I could just do this by saying, just try to be authoritative about it. So when you're building a spherical coordinates, you need a rho squared sine of phi in your integral. I bet for the most part, students just be like, oh, all right. Then if people ask about it, I'm like, it's the same reason that we had to have r in our cylindrical coordinate. And students would be like, oh, all right. Then they'll say, hey, you never explained that either. And I'd be like, oh, moving on. So I was always wondered if I could do this by authority, but I'm not sure. Any questions? All angles are going to be in radians. Save degrees for physics class. I'm just kidding, physicists. Don't at me. Any questions? Comments? Snide remark? It's tricky because I have calculus classes, which means my calculator should be in radians, but I also have a trig class, which means I have to have sometimes the calculator. So, thought about just carrying two calculators, but that seems kind of ridiculous. Although I do find it amusing that my graphing calculator is the calculator that I definitely don't use for graphing. It is terrible at graphing, but it is so good at other things. Like if you've been through linear algebra, you know what I'm talking about. Like all that, find the reduced echelon form of the matrix. Your calculator does that. And your calculator does that better than any app or website that I've seen. Unless they have an app that can scan a handwritten matrix, figure out what it says, and find the reduced echelon form, then they are still behind the TI-84 in finding the reduced echelon form of the matrix. If you don't have one, you should get one. Questions? Comments? Snyder, how's everybody? Okay. Here's the good news. These are spherical coordinates. If you're wondering if these are going to be really good at describing spheres, you are absolutely correct. If we want to describe the volume of a sphere, just like a rectangular solid is the intersection of three intervals in rectangular coordinates, the intersection of three intervals in cylindrical coordinates will be a cylinder, or like a part of a cylinder. The interval of the intersection of 3 intervals in spherical coordinates will make a sphere. So we can describe a sphere of, let's say, radius 3. Rho will go from 0 to 3. Theta will go from 0 to 2 pi. Phi will go from 0, that goes up at the top of Z, and down to pi. We can describe a sphere in spherical coordinates. We can describe a sphere with 3 intervals. Intervals of constant, which means I can switch them around. By convention, although theta can be anywhere, 0 to 2 pi, we could also go from 2 pi to 4 pi. By convention, we say, let's just use that first circle. Let's go from 0 to 2 pi to go around that circle. Even though we can interpret a negative value for rho, we're just going to start rho off at the origin and use positive values. And even though phi can go all the way around, we don't want to double up because we've gone all the way around with theta. So theta is how we're going to get front, back, side to side. We'll get top and bottom just by going from 0 to pi in the angle phi. If we go past pi, then we're kind of like doubling up on stuff we've already gone around on. So by convention, theta will go from 0 to 2 pi, and phi will go from 0 to pi. Any questions? How's everybody? Okay. With my glasses, I can't see the paper. Without my glasses, I can't see the clock. I can actually kind of see the clock without my glasses, but there's a glare right there in the clock, and my eyes aren't good, and on both sides. And my eyes aren't good enough to see what's going on. TLDR, your spherical triple integrals and spherical coordinates need rho squared sine of phi. The reason why is that d theta and d phi need to be turned into distances because those are angles. Because dv needs to be a volume, which is a distance times a distance times a distance. The reason it's a rho and a rho sine phi is this picture right here. So start at the end, work your way back for the reasons. Okay. If you're not okay with spherical coordinates, that is the correct answer. Of course, you're not okay with spherical coordinates. This may be the first day you've ever even seen spherical coordinates described. So tomorrow we will practice with more cylindrical coordinates and spherical coordinates, maybe even some polar coordinates. But for today, that'll do it. That's it for today. I'll see y'all on tomorrow. Everybody have a good day, and thanks for playing.